So you should be able to see my Microsoft Word window with the file that's called sample questions. There's also an answer sheet for this as well. I'm not going to open the answer sheet right now, so that we can go over this together. And in the meantime, maybe you can type, as I talk about it, maybe you can type answers into the chat box. Okay, so which type of data, categorical, discrete, and continuous? Categorical, same thing as nominal. In other words, it's a name or a category. Continuous, a number scale, blood pressure, weight, BMI, and discrete is also numerical, but it's usually for small numbers, small discrete whole numbers, such as number of siblings, 2, 3, 4, 5, and so on and so forth, right? So it's a number, but usually a number that's an integer and is a relatively small range of numbers. Okay, so let's take a look at these three categories. Now, I just want to point out categorical can also contain categories that have some hint as to relative values. For instance, a grade scale, A, B, C, D, is categorical. In other words, an A is a category, B is a category, C is a category. Just like good, excellent, good, fair, poor are categories. But those categories have order. In other words, excellent is better than good, is better than fair, is better than poor. Doesn't mean that we can define exactly how much better. Like in other words, is excellent and good? Is there more of a difference between excellent and good than between fair and poor? We can't really define that, but we can define the order that they're in. They're a special version of categorical that's called ordinal, categorical and ordinal. Okay, so just so if that comes up in any of these, we'll know that. Okay, so occupation. Okay, what kind of variable is that? Okay, so I'm going to give you a second to get your input, and then I'm going to tell you what I think. A little bit of lag. Okay, good. Categorical. You're right. Categorical. How about social status? Lower, middle, upper class. That sounds like the categorical that I was just talking about. It's categorical, but it's also ordinal. How about statewide murder rate? Murders per 100, per thousand, or 100,000? Yeah, probably more like 100,000 population. Hopefully, these days. So that would be numerical. County population size, okay, number of people. That would, even though it's a whole number, that would also be a continuous or numerical variable. Population growth and percentages, 1.3%, 30%, 15%. That is also numerical. Community size, rural, small town, large town, small city, large city, categorical, but again, ordinal as well. Annual income in thousands of dollars. Well, that's numerical or continuous. Attitude towards affirmative action, favorable, neutral, or unfavorable. You know, I wouldn't really assign a value to those. I mean, who's the judge whether favorable is better than neutral, is better than unfavorable, right? So I would just call that simply categorical. Okay, you guys agree with me on those? Any of those that you don't agree with me on? Any of those that the answer sheet doesn't agree with me on? Have you guys looked at the answer sheet? I'd be curious. I'm going to check what you're on. Sure. Okay. Emergency clinic. Now, almost always when we go for this first exam, it's likely that you will get an example of, you guys remember what kind of chart this is called? The left axis, the y-axis is the frequency, the number of people within that range. On the x-axis, right? Number of patients treated per day is on the x-axis, and the frequency, the number of patients that were treated, how often that occurs, how often they treat that number of patients is on the y-axis. A little confusing, isn't it? Right? Emergency clinics collected for 30 days, so there were 30 days represented here. Right, so this is one day. This is one day. This is this is 3 days. This is 6 days. At least one patient was treated every day. You can see that every day at least one patient was treated. This produced a list of 30 numbers, each number representing the number of patients that were treated on the night shift that day. How many days were there more than 8 patients treated in the emergency clinic? Okay, well, let's take a look at this. Number of patients treated per day. Let me see if I can't blow this up a little bit. I don't have a. I'm gonna have to do it. I'm gonna have to do this the hard way. Here. And zoom. Oh no, went the wrong direction. Let's try 200. I must have been on 200. Let me go a little bit further. Okay, I think that would make it a little bit more legible. So what do we have here? We've got 0, 1, 2, 3, 4, 5, 6. This is number of patients treated per day. And we're interested in the number of days that more than 8 patients were treated in the emergency clinic. So how many days were 2 patients treated? Well, on 2 days, 2 patients were treated. How many days were 3 patients treated? Well, on 5 days, they treated 3 patients. How many days did they treat? 8 patients. On 3 days, they treated 8 patients. How many days were more than 8 patients treated? Well, on these 3 days, 9 patients were treated. On these 3 days, 10 patients were treated. So that's 6. And on each of these other 3 days, 11, 12, and 13 patients were treated. So you have 6 and 3 is 9. There are 9 days in which we treated more than 8 patients in this clinic. You guys agree with that? Are you okay with that? I'm going to wait for a reply. It's a little bit of a confusing histogram, isn't it? You have to read the histogram and excuse me for the cough. I'm drinking a little bit of coffee and it went down the wrong way there. So yeah, if I were to ask you what percentage of the days, okay, what percentage of the days were fewer than 6 people treated? What percentage of the day? Remember, this represents 30 days. In fact, if you add them up, 2, 5, 3, if you add all these up, it adds up to 30. You find it up to 30. What percentage of the days were fewer than, I'm going to rephrase that, fewer than 5 patients treated? Okay, well, we had 2 days when 4 patients were treated, 5 days when 3 patients were treated, and 2 days when 2 patients were treated. So 2, 4, and 5 is 9. 9 out of 30 days, we had fewer than 5 patients treated. So for 9 out of 30 days is, I guess, about 30%, a little less than 30%. So whatever that comes out to, that would be the percentage. Let me ask you another one. What's the given that they treated more than 6 patients? What's the probability that they treated 13 patients? Okay, well, given that they treated more than 6 patients, well, that's a conditional probability. So we're only interested in the situation that involves the condition being satisfied. So more than 6 patients would be 7, 8, 9, 10, 11, 12, 13 patients treated on those days, right? So we're only interested in 2. That's 3 times 3 is 9. 2 and 9 is 11. And 3 is 15. Only these 15 days. And how many of those 15 days did they treat 13 patients? Well, only one of the 15 days. So the probability of treating 13 patients, given that you treated more than 6, given that it was days when you treated more than 6, is 1 out of 15. So that would be a conditional probability. Little twists on the questions and stuff like that. Bar chart, a body weight involving 50 individuals. What percentage of individuals weigh more than 140 pounds? Okay, we got four, we got four, we got five. So what percentage of people here weighed more than 140 pounds? Well, how many people were here? There are 50 individuals. And so you can get 4, 10 here, and 2 and 3 here. So that would be 18 and 3. 18 and 3 is 21, and 9 is 30, and 38, and 7 is 45, and 5 is 150. So this is your 50 people here. The frequency is the number of people. So given that there's 50 individuals here, what percent of individuals weigh more than 140 pounds? Well, out of the 50 people, 7 and looks like 5. So it looks like 12 out of 50 weigh more than 140 pounds. So 12 out of 150, 12 over 150 is 24%, 0.24 or 24%. Okay, so let's move on to the next one. In a study investigating the causes of death among people with severe asthma, data were recorded from 5 patients who arrived at the hospital in a state of respiratory arrest. Breathing had stopped, and the subjects were unconscious. Heart rates of the 5 patients upon admission were 140, 40, 120, 136, 104. Calculate the mean and median heart rate for the 5 patients. So how would we calculate the mean? Well, there's 5 patients. We take these 5 numbers, add them together, and divide by 5. Of course, the mean. Well, what's the median? The median would be the middle value. So if I were to put these in order, it would be 40, 105, 120, 136, and 150. So the median would be 120, 120, right? The middle value. Okay. Discovering that the second patient's heart rate is 40 was misread. Should have 40 instead of 40. Recalculate both the mean and the median of the corrected data. So if we change that to 140 and we add them together, divide by 5, we have a new mean, right? Okay. Now what about the median? Well, if this is 140, then 150, 140, 136, 120, and 104. The median now, the middle value is, do I get this right? 150, 140, 136. The middle value would be 136 instead of 120. Does this mistake have a greater impact on the mean or the median? So what do you think? Usually, when you make a mistake, the mean is more resistant to change than the median is more resistant to change than the mean. Okay, when you have extreme values. Let's take a look at this. Let's actually do it. 150 plus 40 plus 120. Oops. I'm going to do 110 plus 10 plus 136 plus 104 equals 550. Divide by 5, and it's 110. Okay, 110 is the average. Now, what if I change that to 40 to 140? And do this again. 150 plus 140 plus 120 plus 136 plus 104. That is at 650 divided by 5. That turns out to be 130. So the mean really went up quite a bit, right? From 110, it went up 20. Where before, the median only went from 120 to 136. So the median was more resistant to change than the mean was when we had that extreme value. See, and that's usually typical. This is like kind of a trite example of it. It only has 5 numbers in it. But those are the breaks. Okay, somebody asked a question about this particular one. Okay, in 1986, this is one of the questions that are one of those 4 questions. So I'm glad this came up now. I'm going to try and make sure I get to all 4 of those questions. even if I have to break away from this. In 1986, the U.S. Federal Reserve sampled 4,000 households to estimate overall net worth of a family. Excluding some outliers of extremely wealthy individuals, they reported the summaries 44,000 and 145,000. Which one of these was the mean and the other was the median? Which do you think was the median and why? Okay, so let me ask you guys, which of these two do you think is the mean, and which of these two do you think is the median? You can just tell me which one do you think is the median. Do you have an opinion on that? Okay, what 140? Do you think that's the median? I don't think so. Let's think about this. If we looked at what the average income would be in the United States, right? You got a lot of people that are in the middle class, right? You got a lot of people that are in the middle class, and you got not so, and you got fewer and fewer people that are extremely wealthy, right? So it tends to be skewed to the right. Now out here you got William Buffett, and you got Bill Gates, and you have what's his name from Amazon. So you have those guys. They like got rid of those. But in the meantime, the top 1% of people in the United States make much more than the rest of the population as a whole. So the average, when we have a small percentage of people making a lot more, even with these guys excluded, making a lot more than the rest of the population, that means that this distribution is skewed to the right. This is called skewed to the right. And what happens when you skew something to the right? Well, in a normal distribution, in a real normal distribution, the mean and the median would be the same thing. They'd be in the same spot, right? But when you have high values, when you skew the distribution to the right, positively to the right, high numbers, right? What happens is the average gets pulled away from the median rather. So the median stays down here, but the average or the mean gets pulled over to the right. So hence it's skewed to the right. So the 44,000 was the median, and the 145,000 was the average. If I asked you for, let's say, what's the average price for a one-bedroom apartment in all 5 boroughs of New York City? Okay, I would guess that distribution looks like this also, right? And why does it look like this? Well, because most of the people that are in one-bedroom apartments in New York City are paying, I'm going to make a wild guess, paying about $1,500 a month in rent. But you have some people in Manhattan, in downtown Brooklyn, and so on and so forth, that are paying much, much, much more, right? So the median, the middle value might be 1,500, but the average rent though for an apartment in New York City might be more like 3,000, maybe not that much, maybe $2,500, right? But a lot of people are paying a lot more than that at this end. So the median tends to be resistant. Now, what about premature births? What about the number of days of gestation? Well, that might be the opposite, right? Because you may have a lot of babies that are born prematurely, but not nowadays they induce labor and so on. But you usually get a lot of babies that are born way past their due date, right? Because of them that induce labor and so on and so forth. So that's a distribution that's skewed to the left. In other words, the average gestation might be, let's see, 30 times 9 is 30 times 9 is 270. The average gestation might say is 270 days, right? But, excuse me, the median might be 270 days, but the average might be lower than that because it's being pulled down by premature births, which could be a lot less than a normal gestation period. right? So in that case, it's skewed to the left. Does that make sense to you? Is it safe to say smaller number will lose me? No, in this case, the median is the larger number, right? Because it's skewed the opposite direction, right? So the important thing to understand is that the extreme when you have extreme values, right? Like a small number of people that are extreme values, if they're low numbers, if the extreme values are on the low side, they pull the mean to the left, away from the median, so that it's lower than the mean is lower than the median. But if the extreme values are on the right, higher, right, then you tend to pull the mean to the right higher than the median. Sasha, does that make sense for you? Are we all comfortable with that? Okay, good. I'm glad, because that's an important point. Oh, it should certainly come up on the exam. So keep that in mind. Okay, good. So suppose that 3% of the people in the community of adults have attempted suicide. Suppose that it's also known that 20% of the community are living below the poverty level. These two events are independent. If these two events are independent, what is the probability that a person selected at random from the community will have attempted suicide and be living below the poverty level? Now, we're making a big assumption here, right? We're assuming that they're independent, that there's no association between poverty and suicide attempts. So if they're truly independent, then we take the 3% and multiply it by 20%. 0.03 times 0.20. So the probability that a randomly selected person would have attempted suicide and be living below the poverty line is 0.03 times zero point 0.2, which is 0.0006, 0.6%, right? So if you want to just do that mathematically, clear, okay, 0.03 times 0.2 is 0.006, or 0.6%, 0.006. Okay, that's assuming that they are independent. Well, let's say we actually did a survey and we found that the probability that in this population, we randomly selected many people, and we found that the probability that someone attempted suicide and lived and was living below the poverty level is actually not 0.006 when we did a big survey sample this population, but it turns out to be 0.015, 1.5% instead of 0.6%. What would that tell you? That would tell you that these two factors are not dependent. In other words, there's an association between being likely to attempt suicide and living below the poverty level. So if we actually did, and this is the result that we got, when we expected this result, then that means that they're not independent. That living below the poverty level makes you more likely to attempt suicide. They're not independent of one another. Okay, so yeah, keep an eye on stuff like that, because that's also kind of a tricky question that comes up every once in a while. Maybe phrased a little bit differently. But one of the things that you can think about is one of the tests for independence would be that what percentage of the time in the population do those two things occur at the same time? In other words, that let's say a person's red-haired and left-handed, right? So if 40% of the population is left-handed, and 10% of the population has red hair, then you would expect, if they're independent, 40% times 10%, about 4%, 0.04, 4% of the population would be both left-handed and be redheads, right? But if you do a survey of the population and it doesn't come out 4%, then you say to yourself, gee, it doesn't seem like those two things are really independent. It should have been 4% of the population was both of those at the same time. and it's more or it's less would suggest that they're not really independent. Maybe there's, who knows why? Maybe there's a genetic association. Maybe left-handed people like to dye their hair. Who knows? But that would demonstrate that at least it's not independent. Okay, refer to the table below. What proportion of women made more than one visit to the obstetrician's office during an uncomplicated pregnancy? I think this might have come up, right? I'm not sure. Okay, so this is the only tricky thing here is instead of the number of women, like in other words, how many women made, this is also kind of a histogram except in chart form. How many women made no visits to the obstetrician's office during their pregnancy? And with a histogram, this would have been, say, a number. It would have been like 10 women, right, or 20 women. How many made one visit? 20 women. How many made two visits? 50. How many made three visits? 10, right? Instead, they're looking at the fraction of women in their sample that went. 2% of the women, not 20, but 2% of the women. 2% of the women went once. 50% of the women went twice, and 10% of the women went three times. Right. So they're looking at it as proportions of their sample or population. What proportion of women made more than one visit? Okay. Well, 5% went twice. 10% went three times, so 60% went more than once to visit the obstetrician. Okay, all right, so that's another way that you might look at that. What percentage of people, a fraction of women, had fewer than three visits? Fewer than three visits would be 20%, 20%, 50% would be 90% of the women went fewer than three times. Okay, so now, how about a conditional probability? Given that a woman visited an obstetrician during her pregnancy, what's the probability that she went three times? Well, given that the given part says that she visited an obstetrician at all, so that lets out the zeros, doesn't it? So that means that given that it's one of these three, that is these from this group here, given that it's from this group here, which is 80% of the population, what's the probability that that woman went went three times? Well, 10% of the women went three times out of the 80% that went at all. So 10% over 80% would be 0.125, where 12.5% of the women that went to the obstetrician went three times, right? Conditional probability, right? Condition says that this only ones that we're considering, and we're interested in what percentage of these that this is. Okay, again, conditional probability. Okay, so now we're going to get into. I just want to get a look at these questions again. Okay. Oh, yeah, we covered this one. Let's put that one aside. If there is time, we could review some additional probability. I think we're about to get into that. And diagnostic tests. Yeah, we got to make sure we got to get to some of that. Really calculate probability of standard. Yep, we're going to get into that. That's part of that question. And okay, one certain community. Oh, this is a specific one that we're looking at here. Oh, this is a tricky one. Okay, good. I'm glad somebody brought that question up. I'm going to put that aside here for now. Okay. So let me get back to this. In fact, this is part of it, but this is the second one. I'm going to do this one first because it's a good lead in to this next one. The scores on the psychomotor development index, a scale of infant development, are approximately normally distributed with a mean of 100 and a standard deviation of 15. An infant is selected at random. What's the probability that that infant's PDI score is 100 and exceeds 103? So I'm going to get a fresh piece of paper here. Okay, mean is 100 and the standard deviation is 15. So I'm going to sketch this out. Again, I like to sketch this out because it helps me understand what's going on. Means 100. The standard deviation is equal to 15. And we're interested in what percentage of children, infants, scored above 103. Okay, tell me if I got that wrong. This is the area that we're interested in right here. Okay, so how do we find out what that area is? Well, we know that the mean and the standard deviation from our uh, 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 empirical rule, we know that if you have the mean, if you have a one standard deviation below and below, 68%, 95%. Unfortunately, this isn't an even number in terms of the z-score for 103. So what's the z-score? How many standard deviations above 100 is 103? Well, I'm actually going to use my little formula there. Z is equal to x minus mu over sigma. And that's equal to 103 minus 100. Okay, notice it's a positive number, which I would expect because it's on the right side of the mean, over 15 is equal to 3 over 15 is equal to 1/5 or 0.20, 0.20. That's my z-score right there, right, z. So what area is this? How can I figure out what this area is? Well, I can either use Excel or I can use my z-table to find the area from 103 or z-score plus 2.0 to the left. And once I found that area to the left, I can just subtract it from 1. It'll mean that I've been left with this area here. So let's do it using the table. See if it comes up. Again, you can use the one in the book. You can. I usually post this on book. I'm sure this is going to be all over Blackboard by the time you take the test. Okay, so here is the negative z-scores, right? Those are the ones that are to the left of the mean. I don't need that one. This one is the positive z-scores. So I want a z-score of 0.2, 0.2, and what's the third digit? Well, if it was 0.24, it would have been 0, 1, 2, 3, 4. I would have gone across here to get to the third digit, and it would have been this number here, but it's not. It's 0.20. It's this number right here, 0.5793, 57.93, 5793. So this area from here down, is 0.5973, or almost 60%. So that means that this area is going to be, since this is about approximately 60%, this area is going to be about 40%. Okay, the percentage of children that would have a score of 103 or above would be about 40% of the children. In other words, I could also phrase it that the probability of me choosing a child at random that has a score greater than 103 is 40%, because 40% of the children are above that score. Okay, actually, the real value is really 1.0000 minus 0.5973, which is going to be 721 0 4 0.4027. I think that's right. Okay, so this really is 0.4027. Okay, now we may ask you to give us this result as a percentage. Probably not. We'll probably ask you to give it to us as a proportion or a probability, 0.4027. We might ask you to give it to us to the nearest 3 decimal places, or we might ask you to just type it in like that. If you give us the whole thing, that's no big deal. Well, if we don't give you any kind of direction at all, why not just put the whole number in? Okay, so now let me just show you in Excel. We could do the same thing. And I can do this 2 ways in Excel. Remember, there's a chart, a PDF file and an Excel file that's on last week's lab session, right, that you can use. Oops, I made a mistake here. I'm looking at the wrong thing. Let me get rid of this. Okay, there's two ways I could do this with Excel. I don't need that right now. Give me a new page. Okay, and let's zoom in here. Okay, so one way I could do it is use this function norm s dist parentheses. When I hit the parentheses, it's going to give me a little bit of help. It says, oh, now give me what the z-scores that you're working with. Well, the z-score I'm working with is a positive plus. You don't usually have to put the plus in. The minus you would have to put in. But you don't normally have to put the plus in. Zero, I'm going to do it anyway, 0.20, right? And I'm going to hit enter, and there's my 57.92. And if I want to find my area to the right, that always gives you the area to the left. If I want to find the area to the left, I just say 1 minus the value in this square. And it comes out to me, my 42. Oh, excuse me, 0.59. Did I look at the right number here? Oh, it was 5793, and this is 42%. Okay, now, you guys let me check the chat box. How did you get 60 and 40%? Well, because I had written 15%. I just rounded it off. I was talking about rounding it off. That's where I got that. But the actual number should have been 42. Actually, should have been 40, 57, 93, 5793, which is which is about 58%, and this would be 42%, roughly, right? Just rounded off. But again, just when you do it, do the math right. I actually I did the math right. I just remembered the numbers in the wrong order. I got that slightly dyslexic mistake that I made there. I reversed the 7 and the 9, but make sure you get the numbers right. You go over it carefully. You get the number. You don't rush like I did. Okay, so that's one way of doing this. The other way is there's a function in here that was norm s dist, norm standard distribution, norm s dist, and it asks you for the z-score. If I used a slightly different function called norm dist, right, and I hit open parentheses, now it's asking me for the x value, the mean, the standard deviation, and cumulative. Now, for this function, you always use true for cumulative. And what was that? Well, that was the value 103 was the value x, what we're interested in, the percentage we're interested in. The mean, which was 100, comma, the standard deviation, which was 15, comma, and true. And this should give us the same percentages as we got before. And indeed, it's 57.5792 again. And again, just equals 1 minus that value. It's always giving you the value to the left. In this case, we're asking for the value to the right. Are you guys okay with that? Even though I made that silly math error, or a silly transposition error, really. It wasn't so much a math error as I misremembered the numbers. If you have the z-score, and you want to, if you've already calculated the z-score and you want to figure out the area, you use norm s dist, right? Because it's only going to ask you for the z. It's going to ask you. Here, take a look, and it will help you, right? Equals norm s dist parentheses. Notice here, it's probably pretty small on your screen, but notice there it says norm s dist, and in parentheses it says z, looking for the z-score. Okay. On the other hand, norm dist parentheses asks you for the x value, the value you're looking for, like 103 in this case, the mean, the standard deviation, and then to remind it to say true or cumulative. Okay, so in fact, in this case, norm dist would have saved us some time, right? Because we wouldn't have had to calculate the z-score separately from that formula that I drew on the board. Okay, so I want to get on to the next one. Oh, no, actually, let me finish this up. Probability that an infant's PDI score was between 93 and 103. I'm going to have to clean this up now. Okay. Remember that this was 5793. Okay, good. I'm going to do a new 5793. I'm talking to myself when I say remember. 5793. Okay. This is the mean, which is 100. Standard deviation, which is 15. And 103 was a z-score of plus 0.2, right? And this area was 0.5793, almost 58%. And this area in here was 1 minus that, which was 0.4207, I think. 7. That looks right to me. Okay, that's what we just did last. That's part of the problem. Now it's asking, what's the probability of infants' PDA score is be between 97 and 103? Oh my goodness! So now we have another question here, and this time we're looking at the value 97, and what we're interested in the area in here between 97 and 103. Wow. Okay, this is very interesting. Let's take a look at this. All right, so let's see what the area, I always have to calculate to the left. So let's see what the z-score is for 97. So the z-score for 97 is equal to x minus mu over sigma is equal to 97 minus 100 over 15. And that's equal to negative 3 over 15. And that's equal to negative 0.2. So now I got to go back to my table or my Excel spreadsheet and look at the negatives. Negative 0.020 is 0.4207. So this area to the left here is 0.4207. So this area is 0.4207. This area is 0.4207, right? And the only thing, if I look at those two areas, the only thing that's left is the area that I'm interested in. The probability of an infant being between 97 and 103. Probability that they're below 97 is 0.4207. Probability that we just figured out that they're above 103 is 0.4207. So this area in here is going to be, let's see, 0.4207 plus 0.4207 is 0.8414. And the only thing that if I subtract that from 1, this area that I need to figure out is left. So 1 minus this. 1 minus this is going to be 0.159686. 0.1586, I think, right? I'm pretty sure. So, I'm not going to get the calculator out to do this. So this is going to be my answer. It's going to be 0.1586. Well, look at this. What a coincidence. 0.4207 is this area, and 0.4207 is that area. Not such a coincidence. Notice that the z-score here is plus 0.2, and the z-score here is negative 0.2, right? These things are symmetrical. Normal distribution is symmetrical. So the area to the left of negative 0.2 is the same as the area to the right of positive 0.2, right? So it's not such a coincidence that these two numbers came up the same, that these two areas came up the same. Okay, so let's take a look at the next part of this problem, which is find the z-score for a PDI of 90. Would you be surprised to randomly choose a child and find that he had a PDI of 90? Okay, so where would 90 be? 90 would be way down here, right? Okay, we're looking at a PDI of 90. So what is the z-score for a PDI of 90? So z-score is going to be equal to 90 minus 100 over 15 is equal to negative 10 over 15, okay, which is equal to negative 0.6666, and so on. I'll round it off here on the third one. Since the table only has 3 decimal places, actually 2 decimal places, and I'd call it 0.66. I'll just round it off there. Okay, so the z-score for this, for 90, is 0.66, negative 0.66, about 2/3, right? So let's go to our table. Look at our negative z-score. Negative 0.66, well, negative 0.06 and 6 or 7 is going to be, let's see, 6 is going to be here, 7. I'm going to round it to 0.67. That's closest to 2/3, I think. It's going to be 0.2514. It's going to be about 0.25, 0.2514. So the probability of getting an infant whose score is 90 or lower is 0.25. I forget what it was, 1.4, I'm going to say, right? About 25%, about 0.25 or 25%. Well, that wouldn't be that unusual, would it? If we randomly select an infant, about 1/4 of the time, they're going to have a PDI score of less than 25, less than 90, right? So that wouldn't be that big a surprise. Now, if you had said PDI score of 50, right? Well, 15 minus 100 over 15 is going to be a z-score of negative more than 3, right? So negative more than 3 is going to be way down here. And z-score negative 3 is only going to happen maybe 0.001% of the time, 0.001 or less than 1% of the time. That would be unusual, really unusual. So that's what that question is really driving at, I think. Okay, I want to get to this last question. I'll get to the other stuff on the weekend. I will get to go. Actually, I'm going to stay on a little bit longer here because I want to make sure that we cover one other thing besides this. In a certain community, the response time of an ambulance may be regarded as a random variable with a normal distribution with a mean of 5.9 minutes and a standard deviation of 1.1 minutes. What does that tell you? Well, just right away, I can see that the average response time is 5.9 minutes. And with this standard deviation, it means 95% of the time, they're within 2 standard deviations below this and above this. In other words, 2.2 minutes, right? So 95% of the time, they get there within, subtract 2.2 from here, will be 3.7 minutes up to 2.2 is 8.1 minutes, right? And between those two, 95% of the time. That's my empirical formula. Just in my head, I'm thinking about that. Okay, but what is the problem for, is this I'm going to answer this question first. Is this a population distribution or is it a sampling distribution? What do you guys think? Can you tell from this whether it's a population distribution or a sampling distribution? A sample would be when they actually sample 100 ambulance trips and figure out the mean and standard deviation. A population would be all of the ones that all of the ones for this population. Right? So what do you think? Is this a population distribution or sampling distribution? Anybody want to hazard a guess or tell me how you know? It's really simple. Really, really simple. Remember what we told you about when we use Greek letters and when we use English letters to represent the mean and the standard deviation? Did we use Greek letters or English words to represent the mean and the standard deviation? We use Greek, right? So what does that mean? That means that we're dealing with a population distribution. Had we used X bar, we would have been talking about a sampling distribution. Okay, are you comfortable with that? Okay, good. So pretty simple, right? A lot simpler than it seemed. What's the probability that an ambulance will take at most 7 minutes? At most 7 minutes to respond to a call. Okay, let's draw our distribution. They said this is a normal distribution. It's kind of a weird normal distribution, but kind of a weird example. Okay, so what's the mean? Mean is 5.9. The mean is 5.9, and the standard deviation is 1.1. Okay, and we're interested in 7 minutes. So 7 minutes is on this side. So what's the probability that it will take at most 7 minutes, right? In other words, 7 minutes or less, right? Not more than 7 minutes, but 7. So we're interested in the area to the left of this from that question. Right? See how I'm interpreting this? It will take at most 7 minutes. In other words, what's the probability it'll take less than 7 minutes, or at most 7 minutes, but not more than 7 minutes? So we're interested in this area of the probability distribution, right? So what's my z-score for 7 minutes is equal to 7 minus 5.9 over 1.1. So that is 5.9, that's 1.1, how convenient, over 1.1, and the z-score is a +1, right? So you want to know something, I could go to my table, and I could look that up, but you want to know something, I know that this is 34% in here, and this is 50%. So I know this is going to be roughly 84%, right, or 0.84. Right, from my empirical formula. Remember, one above is going to be 34%. To 34% to be one standard deviation below, to one standard deviation below 68, so half of that's 34. Let's see what it really is from the table. So one standard deviation, 1.00, is 15.1587. So, I'm sorry, that was a negative. The positive end, a positive 1.00 is 0.8413. So this area from here down is 0.8413. Pretty damn close to that 84%, or 0.84 that I was predicting, right? So the probability that it would take at most 7 minutes is 0.8413, or about 84%. Right? Okay. So what's the next question here? And I'm glad somebody brought this up when they posted it, because it's an unusual twist here. If the ambulance service makes 9 responses on a given night, what's the probability that the mean response time is greater than 7 minutes? Is this a population or if the ambulance service makes 9 responses on a given night, what's the probability that the mean response time is greater than 7 minutes? Okay. Which of two are more relevant to number one? If the ambulance makes 9 responses on a given night, what's the probability that the mean response time is greater than 7 minutes? Okay, let me think about this for a second. This population is a 7 distribution. So let me think about this for a second. Is this a bit beyond what we've been talking about? Is this a sampling distribution? Let me just check something in the answers here. I think this might be a little bit, it's either a binomial distribution or it's a little bit ahead of what we're really talking about here. Let's see what we got in the answer sheet for this. Let's see what we're driving at here. Why did we ask that question at this stage? Okay, that is it down. 4. This probably answers the answer. Is this usually probably standard error of this? Oh my goodness! Hey, you want to know something? We haven't covered this yet. I was wondering why this question would be in here. Do not worry about this. We have not covered this yet. Okay, in order to, this is something, the calculation of the standard error is something that comes up later on. My guess is that this group of questions may have been from an exam that was an extra week or two, right? In a week or two, we're going to be covering this, but we have not covered this yet. Okay, this is this is something called essential limit theorem, where we can work with samples, and the sample size will help us. The sample size impacts what our probability of getting certain outcomes is, right? But we haven't started working with this yet. So I'm going to say, let's not worry about this question. Is that okay? I'm not sure who asked that question, but I think for the time being, we shouldn't worry about that part of this particular question because you haven't talked about the central limit theorem or standard error. See that word standard error? That's a dead giveaway, right? That this problem involves something that we haven't learned yet. That's something that's a special value, right? And that's calculated from the sample size and from the standard deviation. See that 1.1 is the standard deviation, and the square root of 9 is the sample size. That's how we calculate that thing called standard error. But like I said, we haven't done that yet. So for the time being, I would stay away from that. Okay. Okay. Okay, so let me move on to a different question, which was I want to at least hit, since you asked about it, I want to at least cover some examples of problems involving diagnostic tests. So let's open that up, diagnostic tests, practice. Okay, so let me zoom in on this a little bit more. Maybe I can just pull this to get it bigger. Yeah, I can. Okay. I see some relief there. Yeah, yeah. I saw that. I said, "Gee, I know how to do this, but that doesn't sound right for this point in the semester." Okay, so at any rate, let's take a look at this. A device that measures blood pressure correctly. Remember, this is like a diagnostic test. Device measures blood pressure identifies 95% of hypertensive individuals. Those with high blood pressure. It incorrectly identifies 10% of normal tensive individual. I like that word. That's a good one. Those with normal blood pressure as being hypertensive. So what does that mean? 85% of the time, it 85% of the time, it correctly identifies who are have a high blood pressure. 10% of the time, it incorrectly says that people that are normal have high blood pressure. In other words, the opposite, the inverse of that, 90% of the time, it correctly identifies people who don't have high blood pressure. 10% of the time, it gets it wrong. It says they have high blood pressure. So the sensitivity is 85%. That's pretty easy to figure out, right? Because it gets it right 85% of the time, says that they have high blood pressure. This is a little bit more of a curve, right? It incorrectly identifies 10% of the normal people as having high blood pressure. In other words, it gets it right 90% of the time, wrong 10% of the time. But they give you a percent that it got wrong. So you got to interpret. That means it gets it right 90% of the time. So the sensitivity, how good it is at picking out people that have high blood pressure, is 85%. And the specificity, how good it is at identifying people that don't have high blood pressure, is 90%. Gets it wrong only 10% of the time. So assume that 20% of the test population is hypertensive. Well, if I start with a sample of 1,000 people from this population, I would expect 20% of them would have high blood pressure, right? Disease plus high blood pressure. So 200 out of 1,000, you would expect to have high blood pressure. 800 of them you wouldn't expect to have high blood pressure. I'm just getting this from the population, prevalence in the population of high blood pressure. Okay, so if it gets it right 85% of the time, those 200 people, 85% of them are going to be correctly identified. 85% of 200 is 170. And 15% of them would get wrong, 30. Right? Gets it wrong, 30. So this is your true positives. And this is your, well, they have the disease, but they tested negative. So these are your false negatives. Okay. Everybody that's in this row is a negative. Everybody that's in this second row is a negative. Everybody in the first row is a positive. Okay, well, what about the people that don't have high blood pressure, those 800 people? 10% of the time it gets it wrong. So that would be these 80 people here that tested positive, even though they don't have high blood pressure. And these are the other 90% of those 800 people that are correctly identified. So that's why that 720 is in there. So what's the sensitivity of this device? Well, it's 85%. And you can see that from here, 170 over 200 would be 85%. What is the specificity of this device? Well, specificity is 720 out of 800. They got it right. For the people who don't have it, 720 out of 80, which is 90%, right? Which we also could interpret from the statement at the top. If a patient tests positive, what is the probability that they are hypertensive? Well, how many people tested positive here? The total number of people that tested positive is 250. Out of those 250 that tested positive, some of them really have the disease, some of them don't have the disease. Only 170 of them actually have the disease. So out of 250 people, 170 of them actually have the disease. So 170 out of 250, that if we divide that out, calculator out, we divide that out, it's going to be 170 divided by 250. It's going to be equal to 68%. So 0.68. What's the probability that a positive test, that a person actually has this disease? Is 68%. It's going to be C. That's called a positive predictive value. If you got tested positive, what's the probability that you actually have the disease? Positive predictive value. Again, that's a conditional probability. Given that you test positive, what's the probability you really have the disease? Okay, what's the negative predictive value? In other words, if you test negative, what's the probability that you're really negative? Well, in that case, 750 people tested negative. Right, total. Some of them were wrong. They really did. So the negative predictive value, if test negative, 96% chance that you are really negative. Right, 0.96 is the negative predictive value. Okay, now let's apply this same thing to a population that has a hypertensive prevalence of 4% instead of 20%. So I'm going to take the same table, right? Table's optional. You can also do this other ways. Okay, 1,000 people, right? Out of 1,000 people, if the prevalence is 4%, you would expect 40 people that actually have the disease. This column means people that have the disease. Well, 85% of the time, it's going to correctly identify people with these 40 people that have the disease. So that would be 34 out of 40 people. It would correctly identify and test positive. 6 would be incorrectly wind up being tested negative. As far as there were 960 people out of the 1,000 in this lower prevalence population that are not hypertensive, right? And 90% of the time we would expect it to get it right. 10% of the time we would expect to get it wrong. So it gets it wrong 1/10 at a time, 96. Gets it right 90% of the time, 864. So now, if a patient tests positive, what's the probability that they're hypertensive? Okay, how many people tested positive here? A total of 130 people. Everybody in this top row tested positive. And out of that 130 people, only 34 really are positive. Only 34 actually have the disease, right? So in this lower prevalence population, what's the positive predictive value? 34 people out of 130 that's tested positive actually have the disease. Chances of you having hypertension if you tested positive is only about 26%, 0.26, right? So we see here. If they test negative, what's the probability that they're not hypertensive? Well, out of 870 people that tested negative, only 6 of them were incorrectly identified as being negative, and that's a false negative. 864 of them were correctly identified as not having the disease. So the negative predictive value, if you're one of those 870 people that tested negative, the probability that you have the disease is 864 divided by 870. And that would be 99% or 99.3 or 0.993 is the probability that you would test negative. Okay. So somebody just did a lot of typing there, and I want to get to that. Okay. Let me take a look at that. Okay. Heart disease is the leading cause of death, resulting in 24% of all deaths. Suppose that 10 people were randomly sampled in a population who died in, see, it's very small here. I gotta blow this up so I can actually read it. Probability, let me get, wow, there's a lot of typing here, my goodness. Okay, no problem. Let me just read it quickly. No, hang on a second. I want to read it. Don't give up on me yet. Okay, heart disease, leading cause of death in the United States, resulting in 24% of all deaths. Suppose that 10 people were randomly sampled from all those deaths. What is the probability at least one of those deaths was due to heart disease? We need to use binomial distribution, to calculate the probability the probability of at least one of these deaths. I think is this the same problem both times? Yeah, it is, I think, right? Okay, so let's take a look at this. 24% of the deaths in 2011 were due to heart disease. Suppose we sample 10 randomly. What is the probability at least one of those 10 deaths was due to heart disease? Okay, so we're going to take this as the last problem. And then we'll pick up again and repost to discussions board if you want me to cover specific problems. And I'm gonna take a look at this here. I'm gonna close this, make a fresh piece of paper, so I can write this down. Okay, so let's see. So let me write this down here. Okay, so what do we know? We know that the probability that a person who died during 2011, the probability that they died from heart disease is 0.24. 24% of all deaths. If I randomly select one person in the death rolls from 2011, probability is 24% that they died from heart disease, because that's the percentage of people that year that died from heart disease. Now, the issue is, what if I sample 10 people, randomly pick 10 people? What's the probability that, was it at least one or at most one? Yeah, I'm going to be putting this video up right tomorrow morning. What's the probability? Let me go back and let's read the question here. I suppose 10 other people randomly sampled from the probably at least one of them, at least one. So in other words, out of those 10, at least one. In other words, 1, 2, 3, 4, etc. All of those people, right? Okay, so now, you remember the binomial distribution? What do we have here? We need to know the trials, the number of trials. We need to know the number of successes, and we need to know the probability of any individual success. Probability of any success on any trial. One randomly selected person is 0.24. The number of people that we're selecting in this group is 10. And the number of successes that we're interested in is 1 or more. In other words, not 0. Right? Okay, 1 or more. What's the probability of getting 1 or more? In other words, the opposite of not 0. The only thing that's not 1 or more is going to be 0 out of 10 people. Right? So it doesn't seem like a very likely outcome, given that what would we expect the most likely outcome out of 10? The most likely outcome out of 10 would be 2 or 3, right? Because 24% of the people, so we have 10 people, 24% of 10 is about 2 or 3, right? It's 2.5 roughly, right? About 2 or 3. So we would expect most likely outcome would be 2 or 3 people out of those 10 people died from heart disease that year. Okay, so let's pull up Excel and do this problem. It's a binomial distribution problem. Why is it binomial? Because there's 2 possibilities here. They died from heart disease, or they didn't die from heart disease, right? There's no other possibilities, right? So it's a choice of those 2 things. So I opened the old version, but that's okay. I don't even know why I still have this here. So I'm gonna here. What are the possibilities? Out of those 10 people, we can have none, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 out of 10 people. 10 out of 10 could have died from heart disease. Not likely, right? If I pick them randomly. Okay, so what's the probability that none of them would have died from heart disease? That's going to be equals binom dist parentheses, and it wants to know the number of successes. Well, for 0, it's 0. The number of trials, 10 people. The probability of success for any individual person is 0.24. And cumulative. Since I'm only interested in 0, the probability is 0. I'm going to type in false there. And I'm going to close the parentheses. The probability that that we won't get anybody that died of heart disease from a random sampling of 10 people is 6%. Is roughly about 6%, or really more accurately 0.064, right? So what's the probability that one or more people would have died from heart disease? Well, it's going to be equal to 1 minus this value. Okay, it would be 93.5, 93.6, or 0.936 is the probability that one or more, right? Because the only other possibility is none. Okay, now what if I had asked you what's the probability that 2 or fewer would die from heart disease? Well, there's 2 ways I could do this. I could say, oops, ran away on me. Binom dist, parentheses, the probability for 1 is 1, 10, 0.24, false. And that's going to be that. And for 2 people, it's going to be binom dist, parentheses, 2, 10, 0.24, false. And that gives me the probability for what's the probability of exactly 2 people out of 10? Exactly 1 out of 10. Exactly, 0 out of 10. Right? So if I ask you probability that 2 or fewer people would have died from heart disease, I could just do all of those and say false and get only a specific probability for that one outcome. But if I then ask you what's the probability of 2 or fewer, it would be the sum of all of those equals sum, parentheses, of all of these probabilities. It'd be about a 55 or 56% chance that 2 or fewer people would have died from heart disease. Well, what if I had to ask you, what's the probability that 3 or more people would have died from heart disease? 3 or more, okay? So 3 or more is going to be all of these possibilities. Well, all that's going to be is equal to 1 minus the probability for 2 or less, okay? And that's 0.44, okay? That's the probability for all the rest of these put together, right? What if I asked you, what's the probability for less than 5 people out of 10? Well, that's going to be 4, 3, 2, and 1. It's going to be all the probability less than 5 people would be 4, 3, 2, and 1. It wouldn't include 5, right? Because I said less than 5. It's the probability for less than 5 people. Well, that's going to be equal to binom dist, parentheses. Okay, now less than 5. Less than 5 is 4, 10, 0.24, now this time I'm going to say true. When I say cumulative for true, when I say true for cumulative, it's going to give me the probability for 4, 3, 2, 1, and 0, not just for this one probability, exactly 4. So that's going to be 93%. So that saves me the trouble of having to calculate these all individually, right? So that's how we would handle a problem like that.